Welcome to lecture. We're going to continue on here and finish up this gas chapter. And then we will continue on and hopefully get into the next chapter as well, which again, the notes are up there already. Excuse me. If you have any questions, obviously throughout the lecture, feel free to ask them. And we'll definitely get back to those questions when you have them. Okay, so last time we talked about gases, and we've been talking about gases here. And when we finished up talking about the idea of calculating the molar mass of a gas and also the density of a gas, remember that both of those things are really based off of the ideal gas law. And we did see two sort of formulas there that allow you to do that sort of directly. Again, if you sort of can't remember those formulas, you always can use that ideal gas law and sort of just kind of do it as a conversion type problem. And where we sort of left off at the very end here was talking about stoichiometry. So stoichiometry that involves gases are pretty much like basic stoichiometry problems. They could be a basic stoichiometry problem. They could be a limiting reagent problem. But in most cases, what we would have going on is a basic stoichiometry problem. And the main difference is usually somewhere along the way, a lot of times at the end of the problem, you will have to use the ideal gas law, for example, to solve it. So why don't we take a look at this particular problem here. What is the volume of CO2 that's produced at 37 degrees Celsius, 1 atmosphere, and we have 5.6 grams of glucose. So if we just think about the information sort of given to us, we're looking for CO2 here. CO2 is a gas, and we have a temperature given to us. We have a pressure given to us. We don't have moles given to us, but we do have grams, which we can get to moles. And if you think about it, again, we have P, we have N we could get to, we have T, R, which is a constant we could get to. So really for the CO2, we can get to the volume. The problem though is obviously the moles part that we're given, or the grams part that we're given in this case, are not really the moles of the CO2. And that's really where the stoichiometry would come into play here. We need to actually get to moles of CO2. So the first couple of steps here is going to be like normal. We're going to want to start with a balanced equation, which we do have. We want to take whatever they gave us and convert to moles. And really here, again, we're given 5.6 grams of glucose, which is our C6H12O6. So we do have to do that step. We do have to convert it into moles. So we're going to use the molar mass here to do that. And that is 12.01 times 6 plus 12 times 1.008 for our hydrogen from the periodic table, plus 6 times 16 for oxygen on the periodic table. And if we do all that calculation from the periodic table, the molar mass, we should end up with something like 180.2 grams per mole. So you can kind of see that the stoichiometry problem really is like a basic stoichiometry problem here up front. We're kind of doing the same steps. And in this case, we'll get something like 0.0311 moles. But again, here, this is going to be moles of our glucose. And we're not, again, interested in the glucose. We are interested in the CO2. And that's really where the stoichiometry part comes into play. So just like a normal stoichiometry question, we want to go to the equation, and we see for every 1 mole of glucose, we get 6 moles of the CO2. So that's just like the third step in a traditional stoichiometry problem. We're going to take the moles of our glucose. We're going to use the mole-to-mole relationship that we got from the equation to go from glucose to CO2. And again, from the balanced equation, there's 1 mole of glucose, gives us 6 moles of CO2. That is going to really allow us to get the moles of CO2. And if we do that there, multiplied by 6 would be a better move. We end up with 0.186 moles of CO2. 0.186 moles of CO2. And again, a reminder that really the whole reason we're doing all this is because we're looking for CO2, the volume. We had the pressure given to us in the problem. We had the temperature given to us in the problem. R we always have. But really the last thing that we sort of needed to find in order to figure out the volume of the gas was the moles of CO2. But here again, they only gave us the grams of glucose. So at this point, after doing this part of the calculation, which really up until this point is just a basic stoichiometry problem, we now have everything we need to use the ideal gas law here. And that's usually where these type of problems sort of vary from a normal one. Instead of using something like molar mass to get grams, at this point, we will use the ideal gas law. We are looking for volume. So volume would be nRT over P. We do have to make sure of units like normal. And it does look like in this case that the only thing we really need to convert is our temperature. So again, our temperature does need to be in Kelvin. So we want to add 273 to that, and that gets us 310 Kelvin. Other than that, everything else is in the right units. So we'll go with 0.186 moles. We'll use our gas constant, which again is a constant number, hence the name. We'll use our temperature, which we've converted to Kelvin. And we're going to divide all of that by the pressure, which was given to us in atmospheres. So that is good as well. In terms of units, everything here is going to cancel out. The only unit that we'll be left with in this case is liters, which is good because that is basically what we're looking for. Again, the atmospheres will cancel, moles will cancel, Kelvin will cancel. And if we do all that good stuff there, 0.186 times 0.08206 times 310, we end up with 4.73 liters of CO2 should be produced. By the way, that would be our, just like a normal stoichiometry problem, our theoretical yield. Just happens to be in volume. Any questions on any of those steps? So again, gas stoichiometry oftentimes really does follow the same basic steps as a traditional stoichiometry problem. Again, usually in most cases at the end of the problem, it doesn't always have to be the end, but in a lot of cases, it is the end. At the end of the problem, you usually have to use the ideal gas law, and very common, just like we did in this example, a lot of times you'll be asked for the volume of the gas. So usually solving for volume is usually a pretty good way a question is usually worded. Any questions on any of those steps? But it's still the basic sort of 4 steps. Again, as I mentioned, you potentially could have a limiting reagent type problem that's also wrapped up here with the gas law. Would work the same way, just like you would normally do a limiting reagent problem. Again, probably at the end, the only difference would be you would go into the ideal gas law. Any questions on any of those steps there? Okay, and a reminder, if you do have questions, please feel free to ask them. And I think you have an example here, so why don't you give this one a go? We want to calculate the volume of hydrogen gas that would be produced at STP if we started with 5 grams of magnesium. And I think you'll just need magnesium's molar mass if you don't have it, 2431 grams per mole from the periodic table. So why don't you take a minute or two, a couple minutes here, and why don't you calculate the volume of hydrogen gas that we would produce here at STP if we did this reaction starting with 5 grams of magnesium. And then we'll talk about it. Okay, let's take a look here, see sort of how we're doing on this one. So again, this is another stoichiometry problem. We're looking for the volume of hydrogen gas. And that's at STP. So a reminder that when we have STP, it does really stand for some values. The temperature is 273 Kelvin. The pressure is 1 atmosphere. And again, that is basically what STP stands for. And in this case, obviously, we're looking for a volume. We always have R, which is our 0.08206. So you could really see, you could use the ideal gas law here as one way to solve this problem. We have everything we need, again, except for the moles of the gas. We're given the grams of magnesium. So again, this is really where the stoichiometry part comes into play. So we could start with our 5 grams of magnesium, since we already have a balanced equation. We want to convert it to moles, which again is typically the second step that you want to do. 2431 grams per mole of magnesium. And if you get an answer here, you would get 0.20, and we'll call it 0.206 moles of magnesium. Again, that is close to what we want, but remember, we're ultimately looking for H2. And at this point, we really only have information about magnesium. So this is where the stoichiometry part comes into play. And from the equation, we can see that 1 mole of magnesium gives us 1 mole of H2. So really the next step would be that stoichiometry part where 1 mole magnesium would go on the bottom from the balance equation, 1 mole of H2 on top. I think I could do that math there, hopefully. That's going to be 0.206 moles of H2. At this point, we now have H2, which is what we're looking for. And that is sort of the missing number that we need. So now we have that number. We have everything we need. If you like, you can use the ideal gas law here. PV equals nRT. Again, we would be solving for volume, which would be nRT over P. And we would plug in our moles, our gas constant, our temperature, which again is 273 because we're at STP, and our pressure, which would also be 1 atmosphere because we're at STP. Everything is going to cancel out here except for liters, which is good because we're looking for a volume. And if we do that, we end up with 4.61 liters of H2 in this case would be produced. Any questions on that calculation? Now, a reminder that there is actually an alternative way you could solve this problem. And the alternative way you could solve this problem, do it down here, all revolves around this idea here. Because it happens to be at STP, remember that when we're at STP and only at STP, 1 mole of any gas will equal 22.414 liters, which means essentially once we got to this part, we could have took the 0.206 moles of H2, and because we were at STP, we could have done 1 mole equals 22.414 liters. The moles would cancel, and we essentially would get the same number. You might get a 2 here because of the rounding, but you would essentially get the same number as we did above. And again, I think maybe on your calculator there, you might get a 2 at the end because of rounding, 4.61, 5-ish maybe, or 7. So maybe a little slightly different based on rounding, but you essentially get the same answers. So again, remember that if you are at STP conditions, you could use that conversion, but also remember, like we talked about, it is only when you're at STP conditions can you use that conversion factor. If you're not at STP conditions, you have to use the ideal gas law. And if you are at STP conditions, you could do it either way. As you can see, you will get the same answer. But again, if you're not at 273 in 1 atmosphere, you definitely shouldn't use the 1 mole equals 22.414 liters. Any questions on any of that there? This is actually the experiment I think that's coming up. The gas experiment after the titration one, I think. Any questions on any of that? Gas stoichiometry or how to deal with it? Okay, so the next thing we're going to talk about is actually the idea of Dalton's law of partial pressures. So oftentimes when we deal with gases, they oftentimes will come as a mixture of gases. And when we do have sort of a mixture of gases, they do sort of affect the pressure that we see in the mixture. So for example, in our first little container over here, we only have pretty much one gas, which is the red guys that are flying around, which means if we wanted the pressure in this first container, the total pressure, it would be all a result basically of those red gases, that pressure number 1. Now, if we took the second container here and we wanted the total pressure, again, since that green guys that are flying around there are the only gases that are present, the total pressure would be equal to the second pressure there, or P2. But if we mix those two gases together, now what we would have in terms of the total pressure, like what we see on the bottom there, is the total pressure is actually made up of the pressure of our first gas plus the pressure of our second gas. And if you had three gases, it would be plus the third gas, fourth gas. And these are what are known as partial pressures. And they're considered partial pressures because essentially when you add them together, you get the total pressure. So they're each contributing to the overall pressure in that particular container. Now, a couple of ways that we could get sort of the partial pressures, and the most common way that we sort of calculate the partial pressures in a mixture is to use the ideal gas law, PV equals nRT. And as we can see in this nicely drawn picture here, there are a couple of things that pretty much will be the same for every gas that's flying around in that mixture. Because they are all in the same container, they will all have the same volume. So when you think about the ideal gas law, you would be solving for P, which equals nRT over V. So everybody in that container would be the same volume for the gas. And since that container is most likely sitting in the same building on the same table, everybody will pretty much have all the same temperatures. R is a constant, which means if you were going to find the partial pressures of each gas, usually the only thing that will be different for each gas is the number of moles. And then essentially what you do is you solve for the ideal gas law for pressure for each gas individually. Now, we are typically assuming in most cases that these gases are going to behave ideally. And basically what that means is, although there's multiple gases in the same container flying around in this mixture of gases, one of the sort of aspects, or one of the two aspects that we'll talk about a little bit later on, that sort of makes something an ideal gas, one important aspect of it is we assume in an ideal gas situation that although there's multiple gas molecules flying around together, each gas molecule essentially will have no effect on the other, which means they won't be attracted to each other, they won't be repulsed by each other. There's really kind of no interaction that occurs between gas molecules that are basically flying around together. And that's, again, one of the things that make something sort of an ideal gas. And what that means is, even though you sort of have all these different gases in the same container, you essentially could treat each gas separately as if they were there by themselves. And then once you find the partial pressures of each gas by doing basically a separate calculation for each one, to find the total pressure, you simply would add up all the partial pressures together. Any questions on that? And that's what we see here. Most common way to calculate the partial pressure of a gas is to use the ideal gas law. And that is what these top two equations obviously are for when we have a mixture of gas A and a mixture of gas B. And then obviously the total pressure in this case would be the partial pressure of A plus the partial pressure of B. Now, there can be certain situations, just kind of circle it here, and then put a little line there, just having fun drawing lines. But there can be certain situations where you may not be given enough information to actually calculate the pressure using the ideal gas law. And that's where the equation that's in the box, and really these equations here as well, come into play. You could calculate, if you look at this equation in the box, PI is the partial pressure of a gas. So that's the partial pressure of a gas. XI is the mole fraction. So if you remember, I think in the very last chapter, at the very end, we calculated the mole fraction. the mole fraction is pretty much like a percentage without the multiplying by 100. So basically, it's the moles of the gas you're interested in divided by the total number of moles. And PT here is the total pressure. So if you perhaps only have enough information about how many moles of each gas or how many grams of each gas is there, and that's kind of all you're given, along with perhaps the total pressure of the mixture or one of the partial pressures, you could actually use the equation in the box there to calculate the partial pressures, the total pressures as well. So these are two sort of common ways that you can calculate partial pressures or total pressures. And really, the one that you choose is oftentimes dependent on sort of the information that's given to you in the problem. If you have enough information, to basically use the ideal gas law, you should use the ideal gas law. If you feel like you're lacking enough information to use the ideal gas law, you most likely can use this other equation here where you calculate the mole fraction. And that's what this is. Again, this is the mole fraction up here. You take the moles of the gas you're interested in divided by the total moles in that mixture. And again, that will give you the mole fraction. Any questions on that? All right, so I think we maybe got an example, maybe. There we go. All right, so why don't you take a couple of minutes here and calculate this. We're looking for the partial pressures of both helium and neon in a mixture together in a 2.5 liter container at 27 degrees Celsius. And we're also looking for the total pressure. So helium from the periodic table, 4.003 grams per mole. And neon from the periodic table, 2018 grams per mole. All right, so take a couple of minutes here. You should end up with 3 different answers. We're looking for 2 partial pressures, partial pressure both of helium gas and neon gas. And then once you have that, we're looking for the actual total mixture of this, total pressure of this mixture of gases. They're obviously in the same container. So take a couple of minutes and see how you do. Okay, so let's see how we're progressing here. Make sure everybody's at least on the right track. So again, in this situation, we basically have a container, and it's got helium in there flying around. It's got neon in there flying around. And again, we essentially can treat each of those as they're in there by themselves. Again, since they're both in there together, they both will have the same volume, which in this case would be our 2.5 liters. They also will have the same temperature, which would be 27 degrees Celsius. We do need to convert it into Kelvin. So that looks like a 300, I think, Kelvin. We are looking for the pressures of each of those gases. So we're looking for the pressure. And remember, we always have R, which is a constant. So we pretty much have everything we need except for, again, the moles of each of those gases. And that's really where you're going to want to start. So we're going to want to first figure out the moles of helium. And again, from the periodic table, we see that helium is 4.003 grams per mole. We'll also want the moles of neon, doing pretty much the same calculation here, are 5 grams of neon, using the molar mass from the periodic table, which is 2018. And at this point here, we will get for our helium, if we punch in the right number, I suppose, 1.25, it looks like, moles of helium. And for our neon, it looks like we end up with 0.248 moles. So at this point, we essentially have everything we need for each of the gases to calculate the pressure. Again, here we're basically using PV equals nRT, and we're solving for P, which would be nRT over V. And we just want to put everything in sort of correctly here. So the partial pressure here of helium would equal our moles, which is 1.25, our R, which is 0.08206 liters atmosphere Kelvin mole, our temperature, which we converted to Kelvin, 300 Kelvin, all going to be divided by our volume, which is the same for everybody, 2.5 liters. Everybody's going to cancel out in terms of units here. The only one that we'll be left with at this point is atmospheres, which is good since we are looking for pressure. So 12.3 atmospheres in this particular case. Now we will do the exact same calculation for our other gas, which is neon. Really, the only difference is we're going to use neon's moles. Everything else here is going to be exactly the same because they're sitting in the exact same container. So everything's the same, temperature, volume, obviously our gas constant as well. Just like above, everything's going to cancel out except for atmospheres. And if we punch all that in, we get 2.44 atmospheres. Now, when we look at each of these represents, again, the partial pressure of helium. And the bottom one is the partial pressure of neon. Any questions on those calculations there? Now, we are also looking for one other sort of answer, and that answer is the actual total pressure. So in this particular case, the total pressure, because there's only two gases in there, which should be the partial pressure of helium plus the partial pressure of neon. And as we will see here, 12.3 plus 2.44 will give us a total pressure of 14.7 atmospheres. Any questions on where any of those numbers came from? Any reason why? Now, you may see that in this particular mixture, based on the calculation we did, we should see that the major contributor to the pressure in this mixture is actually helium. Yeah. So helium has the higher pressure. It's a major contributor to pressure. And we're going to see a little bit later on why that is, but really a preview is if we look at the molar mass of helium versus the molar mass of neon. Helium is about 5 times lighter than neon, which means it's lighter, and it means, as we will see a little bit later, it can actually move a lot faster than neon. And because it can move a lot faster than neon, helium would be having more collisions and causing more of the pressure that we would see. Any questions on that? All right, so I think we have another example. So why don't you give that a go there. The sample natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If the total pressure is 1.37, what is the partial pressure of propane, which is the C3H8? So see what you come up with in this particular case. Take a moment or two. Okay, so in this particular case, we're given the moles of each of these three gases. So we got 8.24 moles of our methane, we have 0.421 moles of our ethane, and we have 0.116 moles of our propane. In this particular case, we really don't have enough information without making up numbers to use the ideal gas law. Although we do have moles and we do have R, we really have no idea what the temperature is. We really don't know what the volume is. So we really can't go into the ideal gas law. So this would be a case where we would want to use that other sort of partial pressure formula that we saw, where the partial pressure of a gas is equal to the mole fraction times the total pressure. And this one we could use because we do have the total pressure. We do have enough information here to figure out the mole fraction. And I see a number there, which I think looks good. So let's just verify. So the first thing we'd want to calculate is the mole fraction of propane in this case, which is the C3H8. And in that case, we do have 0.116 moles of propane. We want to get the total number of moles by adding them all together, which would be 8.777. And we're going to divide that by 8.77. Remember, it's not a percentage, so we're not going to multiply by 100 or anything like that. So we take 0.116 divided by 8.77. Probably have to punch in that 7. That will give us a mole fraction of 0.0132. And we already have the total pressure given to us, so we can go into here. So the partial pressure of C3H8 would equal our mole fraction that we just calculated times the total pressure, which in this case is 1.37 atmospheres. Really kind of like taking a percentage of the total pressure. And we do end up with 0.0181 atmospheres, which looks good. And our chat box there, so very good. And that would be our partial pressure of propane. We could also do all the other ones as well. We could get the mole fractions of ethane. We could also get the mole fraction of methane. And again, it would be done very similar. For example, the mole fraction of ethane, which it didn't ask for here, 0.421 moles divided by the total moles. Gets us 0.0480. Then our partial pressure of it would be 0.0480 times the 1.37 atmospheres. And again, if you were looking for each of them, you could just do this process again. You get something like 0.0657 atmospheres. And really at this point, you can do that for the last one, which is our methane, the exact same way. Or because these are the only three gases in that mixture, you could add the 0.018 together with the 0.0657 and then subtract it from 1.37, and that would give you the partial pressure of methane. Question on how to use this equation here. So this is a very useful equation to figure out partial pressures, figure out total pressures. Really, again, you just need some way to get to the moles of all the gases in a mixture, and you need some pressure information. So either a partial pressure information of one of the gases, total pressure, but you need some type of information like that in order to use it. Any questions on that particular problem? Okay. Now, another very common way that we collect gas in experiments is in a situation like this. So for example, if we heated up this potassium chlorate, it would generate some oxygen gas. Oxygen gas would follow the tube, hopefully not go outside the tube like my drawing there. And it will go into this collection jar, which usually will have some water in it. And basically, as the gas goes in, the water goes out. of the jar. And you end up with this empty spot, usually in the collection jar. And this empty spot really is not empty. It is really where the gas you're collecting is going to be. And that would be your oxygen gas in this particular case. But as a consequence of how the gas was collected here, it was collected, sometimes referred to over water, saturated with water vapor. Just the reaction itself is going to heat up the water a little bit. And when we heat up the water, we not only get the oxygen gas in there, we also get some water vapor. Which means ultimately we're not interested in the water vapor, but it does sort of come along for the ride, if you will. So this is also a partial pressure type situation where the total pressure in this case would equal the pressure of the gas you're interested in, which in this example would be O2, plus the pressure of water, which is known as the vapor pressure of water. And the vapor pressure of water is usually a value you can find on a table. So you usually will look this up on a table, and you would look it up on this table based off of temperature, and you would find that. And the reason we usually will do this is when we're doing this experiment, for example, in this picture, really the only thing we're interested in is this gas. Although we get some water vapor in there with our oxygen, we're not really interested in the water vapor. And sometimes still refer to this as getting the pressure of the dry gas, because you have to basically subtract off the water vapor pressure. So the pressure of the gas you're interested in would be the total pressure minus the vapor pressure of water at that temperature. And again, that is a value you can find on a table. Where do you find the total pressure? Well, if you're doing an experiment, that's usually your barometer reading. Very badly scribbled there, but that's supposed to say barometer reading. So that would be your barometer reading, like you get off the wall. It's your total pressure. It's basically atmospheric pressure. And you have to sort of do this in these type of problems because, again, you're interested really in just the gas you're collecting, which again, in this example would be the O2. And you have to sort of do this correction factor where you subtract off the water vapor pressure. And that's what we see here. Again, we would subtract off the vapor pressure of water from the table, less the total pressure there will give you just the pressure of the dry gas you're interested in. And here's a table of vapor pressure water. This is not the one from your book, but usually in the gas chapter, you usually will have a table such as this. And again, it's typically a value that you just find in the table. Actually, your lab manual, I think, in the very back, there's a bunch of tables about vapor pressure of water. You also find the density of air and stuff like that. Coming up for those gas experiments, you may have to reference those tables in your lab notebook at the end. So if we look at a problem like this where we have a sample of oxygen gas that's saturated with water vapor, and when you read a problem, those are keywords that you oftentimes will hear in those problems that basically tell you that you need to do some type of correction for the vapor pressure of water. It will say it was collected over water. It will say, just like here in this problem, it was saturated with water vapor. And all those are sort of keywords that tell you that you need to do basically what we were just talking about, that the total pressure is equal to the pressure of the gas you're interested in plus the vapor pressure of water. So in this case, the total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the gas? So in this case, the total pressure would equal the partial pressure of oxygen gas plus the partial pressure of vapor pressure of water, and rearranging would equal our total pressure like we've been seeing minus the vapor pressure of water. So in this case, we would just need to take the 753 torr minus a value we would look up in a table. And by the way, that is really why in this problem, they gave you the temperature. The only really purpose of the temperature here is so you could go to the table and look it up for the correct temperature. And when we subtract it, we get 753 minus 31.824. Gets us something like 721 torr. We're interested, though, in it in atmospheres. So our conversion we talked about at the very beginning, we would divide by 760. And that's going to convert our torr into atmospheres. And if we do that, we end up with 0.949 atmospheres. And that would be the pressure of our oxygen gas. And again, sometimes people refer this to like the dry gas because again, you sort of subtracted off the contribution of water to the pressure in this case. Any question on this type of partial pressure problem? So those are three sort of common partial pressure type problems that you'll come across. One where you'll just use the ideal gas law basically to solve for pressure for each gas. One where you will use the mole fraction, and one where you will use kind of the vapor pressure of water. Yeah, I don't know if anybody else is having a hard time hearing or not. Again, maybe log out or come back in. Sometimes that helps. Hopefully everybody could hear okay, I hope, yes. All right. So we'll continue on. Hopefully it should get better. Sometimes, it does have some issues depending on how many people are on and stuff like that. So hopefully it should be good. If I do sound further away, I'm sorry. Hopefully I haven't changed anything. So hopefully, it'll kind of pick up. If not, maybe adjust the volume on your side. If it is a little lighter in terms of the volume and stuff like that. Sometimes it gets a little kind of picky along the way as you're going. I've had lectures where it kind of pauses as I'm writing stuff for like a long time. So hopefully it should be okay. Again, if not, a reminder that usually nothing's wrong with the volume or the sort of voice part on the recording. So again, you could always go back and look at something if you need to look at it. Is that any better yet? Did it kind of come back? Okay, so hopefully that should help better. Okay, sometimes just gotta give it a second or two, hopefully to sort of catch up. All right. All right. So any questions then on partial pressures? No worries. Thank you for letting me know. It sometimes just happens and stuff kind of goes away, comes back and stuff like that. So, all right. So let's talk about the kinetic molecular theory of gases and some of the main parts here. And again, you should know sort of these main parts. The gas is again composed of these separate molecules that are separated by far distances between them. And one of the things that sort of makes something an ideal gas is the first thing that's listed here. And it's the idea where the gas molecules basically are far away from each other. They're considered points. The volume of the gas themselves is basically small compared to the container at which they're in. And that means that we assume that the gases have a negligible volume. And essentially what that means is, if you think about a lot of the problems that we've come across, we oftentimes talk about the volume of the container that the gas is in. And it's with the sort of the understanding that the gas molecules are flying around consistently throughout the entire container. They're filling it uniformly. But in comparison to the container at which they are flying around in, the volume of the gas themselves are actually very small compared to the volume of the container they're flying in. So in an ideal gas situation, one thing that we don't take really into account is the actual volume of the gas molecules itself. Again, we focus more on the volume of the container. Gas molecules are moving constantly. Again, these collisions, when they collide with one another, they collide with each other. They're perfectly elastic, which means, they bounce off perfectly good. Nothing slows them down or anything like that. Now, number 3 is the second thing that really makes something an ideal gas. So number 3 here and really number 1 here are the two things that make something an ideal gas, and that is the attractive forces and repulsive forces. So although gas molecules can be near each other, in an ideal gas situation, we assume that the gases neither are attracted to one another, nor are they repulsed by one another. They're kind of free to fly around with each other with no problem of interacting with each other. And that's why on those problems that we just did, where we did the partial pressures, the gas molecules, although they were in there as a mixture of gases, we could treat each gas as they were in there by themselves or separate from one another. And the reason for that is number 3. Again, the assumption here is if those gas molecules have no attractive forces or repulsion forces to one another, this gas molecule, for example, would be free just to fly around as much as he wanted. Now, in a different situation, which we'll talk about at the end of this chapter, if there is some type of attractive force between these gas molecules, as this gas molecule at the end tries to fly away, he may feel some resistance because he's being attracted to another gas molecule, or he may kind of fly away a lot quicker because he's repulsed by another gas molecule. And that is the difference between two types of gases that we'll talk about. Pretty much what we've been talking about is an ideal gas. And those are the two assumptions that we sort of think about in an ideal gas situation. There's no volume of the gas itself compared to the container, and there's no attractive forces or repulsive forces between them. When we do have to take those two things into account is when we talk about what is referred to as real gases, which we'll talk about at the end of the chapter here. And real gases, you do have to take those things into account. The last thing of the kinetic molecular theory is the average kinetic energy of a molecule. Gas molecules basically will increase. So that has really to do with temperature. So as we increase the temperature, gas molecules will fly around faster, probably causing more collisions. While if we lower the temperature again, they would probably slow down a little bit, not be flying as fast. So these are just some of the relationships that we talked about here with our different gas laws. So again, just a reminder here, we have Boyle's law, which is the pressure volume relationship. And as the pressure goes up, the volume goes down. And vice versa, as the pressure goes down, the volume will go up. We have Charles' law and Guy-Lussac's law that we talked about. As the volume goes up, the temperature will go up in a constant pressure situation. And as the pressure goes up, the temperature will go up in a constant volume situation. And if vice versa, the volume goes down, the temperature will go down in a constant pressure situation. And the pressure will go down, the temperature will go down in a constant volume situation. We also saw our Avogadro's law that we talked about in terms of their relationships. As the moles of a gas is related to the volume. So as the volume goes up, so does the number of moles sort of proportional to each other, and as it goes down as well. And then sort of the last relationship that we saw here, again, because of that idea of an ideal gas law where there's no repulsion forces, no attractive forces between the gas molecules, That is why when we do partial pressures of mixtures, as we've been talking about, we can basically treat each gas as if they were basically in there by themselves, and then basically just add up the total pressure. Any questions on any of that there? Okay. So the next thing we're going to talk about is sort of the speed of a gas. And we have a couple of diagrams here. Let's just talk about sort of these diagrams. The one on the top left here is all nitrogen gas at 3 different temperatures. And what we see with nitrogen gas at 3 different temperatures is the speed of each of those. So at 100 Kelvin, this is basically the big proportional molecules and their speed. At 300 Kelvin, this is essentially their speed. And at 700 Kelvin, this is essentially their speed as well. And what we see is when we're talking about the same gas and we increase the temperature, we will see the gas molecules start to travel faster and have a higher velocity at which they are traveling, or molecular speed. Now, when we look at different gases, all at the same temperature, we see chlorine has a speed of over here. Nitrogen is kind of about there. And lastly, we see helium, which is over here, have a speed of about here. And what we see is when we look at the different gases at the same temperature, helium is the lightest of these 3. Chlorine is the heaviest of these 3. And we see that helium, which is the lightest, has the higher molecular speed. And that is typically what we see as the molar mass increases. The gas molecules will not be able to fly around as fast as something that is smaller or lighter than that. And it will usually result in a slower speed and thus contribute perhaps to less of the pressure. So to illustrate this and how we could calculate sort of the speed of a gas molecule, we could use this formula here. RMS is what is known as the root mean square velocity. Our RMS, root mean square velocity. And it is equal to the square root of 3 times R, which is the gas constant, times the temperature in Kelvin. This is the molar mass. Now, when we do the molar mass and we use this formula, we actually are going to use the units of kilograms per mole, not grams per mole. And the reason for that is R in this case. R in this case is 8.314 joules per Kelvin per mole. Now, that is a different gas constant than the one that we've been using, which is the 0.08206 number. And it's important because a joule is equal to a meter squared times a kilogram divided by a second squared. And because the joule is basically a kilogram, we need the molar mass to also be in kilograms so everything cancels out correctly. So a couple important things about this formula here. We want to make sure that we use the correct R value, which is the 8.314. And we also want to make sure that the molar mass is in kilograms per mole rather than grams per mole. So if you remember on the partial pressure problem we did, we had helium and neon. So if we did helium and we wanted to calculate the root mean square velocity, right, which is abbreviated as that U type symbol, not really a U, we would take the square root of 3 times R, which is 8.314, if we substitute in those units, we would have kilograms meters squared seconds squared divided by Kelvin and mole times our temperature, and we will do 25 degrees Celsius. So we'll do this at 25 degrees Celsius, which is 298. We would divide it by the molar mass, which is 4.008. But again, we need to convert that from grams into kilograms, and we would end up with 0.004003 kilograms per mole. That is this number right here divided by 1,000 to convert it into kilograms. And if we do all that good stuff there, we would take 3 times 8.314 times 298. And do a little square root on it. And we will end up with something like 1,363. The units that will be left will be meters per second. And that is because the kilograms down here will cancel. The moles will cancel. The Kelvin will cancel. We are left with meters squared over seconds squared, which then when we take the square root of it, will end up as meters per second. So that would be the root mean square velocity for helium, like we saw in that partial pressure problem. Now, if we did it for, where can I do that? Actually, I'll just get rid of that and then kind of drop it in there. Perfect. Give me a second to clear a little bit of space. Perfect. Now, if we do the exact same calculation here for our neon, which is what we also did earlier, if we did the root mean square for neon, it would be the square root of our 3 times our 8.314. Again, joules per Kelvin mole, but it really is kilograms meters squared seconds squared, just to save space. I'm not going to kind of write all those in. Just kind of clear out a little bit of room here. Perfect. We're going to do it at the exact same temperature, so we're going to do it at 298. And we're going to divide it by the molar mass of neon, which was 2018, I believe, is what we used earlier. Again, we need to convert that into kilograms. Divided by 1,000 will equal 0.02018 kilograms per mole. Again, everything is going to cancel out except for, even that's going to cancel. What we'll be left with again in the square root part is meters squared over seconds squared. And when we take the square root of it, obviously it becomes meters over seconds. And if we take the square root of that, we will end up with 607 meters per second is how fast neon is basically flying around. Any question on those calculations? So again, the important thing when you do these calculations is to make sure you use the correct gas constant, which is the 8.314. And you also need to make sure that you convert it, the molar mass, into kilograms per mole. That way, all the units will actually calculate out correctly. You'll end up with meters per second. And what we see here is helium, which is, again, about 5 times lighter than neon. is moving about twice as fast as neon is. And thus, as we saw in that last problem that we did with the partial pressures, it contributed to most of the pressure. So you do need to know about root mean square and how to calculate it. So you do need to know that equation, 3RT molar mass. Again, molar mass in kilograms per mole are 8.314. Any questions on that? Now, another aspect of gases is the idea of gas diffusion. There we go. And in gas diffusion is the gradual mixing of one gas with another based on their kinetic properties. And you can use this equation to calculate things. The R's here are the rates, and the M's here are the molar mass. And in this particular case, you can do the molar mass in grams per mole because you're not doing anything with R. So this one, you can do that. But if we look at these two things, we have ammonia gas, which is coming out of the container. We also have HCl, which is coming out of the container. And when the ammonia and the HCl come together, they will come together and make ammonium chloride when they mix. And what we see by this picture is most of the mixing is happening over here by the HCl, the hydrogen chloride gas. And there is a reason for that. And most of what it is what we just talked about. If we look at the molar mass of NH3 versus the molar mass of HCl, we would expect that the root mean square velocity for HCl would be slower than the root mean velocity for NH3, which means when the NH3 comes out of the bottle, it's moving faster than our slow moving HCl. And that's why when we see the mixing occurring, which is that white sort of cloud there that I just scribbled over, we see the mixing closer to the slower moving HCl or hydrogen chloride. Any questions on that? And again, if you were given some rates, if you're given some molar masses, you could actually calculate either a molar mass, you could calculate how fast one is moving versus another. So gas diffusion is the gradual mixing of gas molecules by the virtue of their kinetic properties. And another aspect of gases is what is known as gas effusion. And gas effusion is the process where a gas under a pressure, and if you kind of pop a hole in the container, the gas molecules will basically effuse to the other side, as we see here. It's the process by, with under pressure, gas from one compartment in a container will basically go into the other container. And we have basically the same formula as we just saw on the other page. Again, here are R's, our rates. These are our molar masses in grams per mole. T here is actually time in this case, yeah? So sometimes in these problems, they will give you, hey, it takes 30 seconds for this guy to get to the other side, while it takes a minute and 20 seconds for the other gas to get there. So, or sometimes they may say gas one moves at a rate of 5 meters per second, while the other one moves at 34 meters per second. So sometimes they may give you rates, sometimes they may give you time. But again, you can use this formula here, which is essentially the same one as we just saw, to calculate either rates, how long it would take a gas to go from one side of the container to the next, or the molar masses of some of those gases. Any questions on those couple of things, diffusion and effusion? We're going to skip that example. And we're going to finish talking about gases here with deviations from ideal behaviors. So everything that we've been talking about up until this point has been ideal gases. So really what we're talking about now is oftentimes referred to as real gases, unlike the fake gases that we've been talking about. And when we get into sort of a real gas situation, we see a lot of deviation from the ideal gas situation. And in the ideal gas situation, if you take the ideal gas law and you take PV over RT, sort of the perfect ideal gas situation would give you a ratio of 1, as you can see there. And if you kind of super zoom in, where we typically kind of deal with, you can see that most gases do behave very much like an ideal gas, right? Because normal pressure is like 1 atmosphere, right? Which is way over here. But when we get into situations of very high pressure and low temperature, for example, which is out here, obviously these are extremely high pressures, which is not normally where we deal with. We see a lot of deviation for gases from that ideal behavior. And when we get into these really large pressures, if you think about really large pressures and volume, right? Large pressure would mean we should have a pretty small volume, right? Which means when we have that very small volume, unlike in the ideal gas situation, where we assume that the gas molecule itself has no effect, the volume of it has no effect compared to the container it's in. When we get to these really high pressure situations where our gas molecules in this really small volume, obviously you can see just from that picture, its volume is very significant, as opposed to if this was more of an ideal gas situation, you know, its volume compared to all this other volume is not that big of a deal, the volume of the gas molecule itself. But when we're only talking about maybe this much volume, the actual gas molecule's volume itself does need to be taken into account. And because of that as well, all the gas molecules in that very small volume at these really high pressures, just by the process of that, if you had more than one gas molecule in that really small volume, you could clearly see by this picture is they got really nowhere to go. They got to come in contact with each other, rather than in the ideal condition where if you have a whole bunch of gas molecules in there, they have a lot more room to really spread out. So they're not really interacting with each other. So two things come into play when we talk about real gases under these conditions. The volume of the gas itself is no longer negligible compared to the volume of the container it's in, because it's now in a very small volume. And because it's in a very small volume as well, everybody is pretty much near each other. So now you're definitely going to get some interactions between these gas molecules where we will see some attractive forces and repulsive forces basically come into play. And under an ideal gas situation versus a real gases, again, the situation where this occurs is these two situations here. When we have really high pressure, so as we were just talking about, under those really high pressures, the volume is going to be very small. So everybody's going to be near each other. The volume of the gas is really important. And then also at really low temperatures. At really low temperatures, our gas molecules are moving slow. Right? This gas molecule is moving slow, which means when those gas molecules come near each other, they're going to be near each other for a much longer period of time than they would be if we were at a higher temperature. So as they're moving a lot slower with a lot less energy, they now will be interacting with each other for a longer period of time. And that's going to basically allow them to interact with each other and have things like repulsive forces and attractive forces come into play. And remember that in the ideal gas situation, those are the two things that we sort of ignore. We ignored the volume of the gas itself, and we ignore basically any attractions between gas molecules. And again, at very low temperatures and very high pressures, those two sort of assumptions really don't hold up when we deal with real gases. And that's what we see. Whoops, come back here. That's what we see here in this graph. Because a real molecule or real gas does take up space, when we calculate something like the molar volume, which is essentially that a molar volume of a gas is that 22.414 liters, right, per mole, we get actually a larger value than that predicted by the ideal gas law at higher pressures. So at lower pressures, everybody is pretty much maintaining. But as we really start to build out into higher pressures, we start to get a difference in that molar volume of a gas. And that's why, again, in most cases, since we're dealing with pressures usually back in this range, we can mostly assume most of the time that everybody's behaving ideally. But if you do get into these really high pressure situations, you will start getting that deviation in terms of the molar volume. And what that essentially means is you do need to take it into account. And one person who came up with a way to sort of take that into account is a guy by the name of van der Waals, hence the van der Waals attractive forces, like dispersion forces and all those kind of things. And he came up with really a correction value that we can sort of insert into the ideal gas law. So taking the ideal gas law, he basically modified it for this volume difference that we see in real gases. So our volume difference in real gases. And he also came up with the van der Waals constant for that, and that is what is known as B. And A and B are van der Waals constants. And they are values that you look up in the table. And those values are different for different gases. So you want to look up the right gas. Now, van der Waals also took into account the other thing that we see deviate from ideal gases, and that is what we see in this picture. Oops, come back. That under these temperatures, these really low temperature values, we do see interaction between the gas molecules. We do see attractive forces and repulsion forces. And at lower temperatures, in this range, we start to really see some deviation between the ideal behavior, which is the red line, and the green line, which is the real gas behavior, when we have much lower temperatures. And that again is for the reason that they are basically moving a lot slower, which means these gas molecules are now going to be very close to each other at these low temperatures. And there is going to be some attractive forces and repulsive forces that's going to happen. And van der Waals also came up with sort of a correction value for that as well, for those intermolecular forces or attractive forces that occur. And that is what is known as van der Waals constant for A. So this is basically the corrective measure that has been done for interactions to the ideal gas law. So van der Waals came up with these sort of corrective factors or ways to correct the ideal gas law. And just to sort of illustrate here, under real gas situations, because they are so close to each other and maybe because of the temperature, they're not going to be moving around as fast from each other. There will be some attractive forces. So again, this red gas molecule, which under the ideal situation would be free just to bang into the container, no problem, now feels some drag back from these gas molecules here. So perhaps it takes longer for it to hit the container. If it takes longer for it to hit the container, we are going to see an effect on the pressure that's going to be exerted by that gas. Because again, in the ideal situation, you could kind of think of the gas molecule as free to fly around, no problem, nothing bad's happening. I'm just actually liking scribbling on the screen. As opposed to here in our real gas situation, it's not going to be as freely able to move around as fast, because there's going to be these attractive forces and maybe some repulsive forces as well that's occurring. And again, that's all going to have the effect on the pressure. So what we end up with is the ideal gas law that van der Waals basically modified for each of these situations to deal with real gases or non-ideal gases. And this is what is sometimes referred to as the van der Waals equation. And you can see it's a very scary looking equation, but it really is kind of the ideal gas law. This is still your pressure in atmospheres. This is still your volume in liters. This is still your moles. Still your volume in liters, still your moles. Still your moles here. Still the ideal gas constant, 0.0206. And that's still your temperature in Kelvin. The difference is we insert these correction values here, the A and B values. And again, this is not a table from your book, but you have a similar table where you can find van der Waals constants for A and B. And again, you can see it is dependent on the gas you're dealing with. So every gas will have basically some different values. And basically, you use van der Waals equation here to solve for whatever you may want to solve for: pressure, volume, the gas constant, temperature. Again, this would be what would be used for real gas situations. Any question on that? So again, you would solve if you had numbers just by plugging and chugging into there. All right, I think that should wrap this chapter, which is good. So that wraps up this chapter, which is chapter 8. This will be the last chapter that will be on your exam. Again, a reminder, your exam will be 1 week from today, and we will take it probably during lecture time, maybe during lab time. We'll see sometime around there. I'll let you know. And it will cover this chapter. It should cover, I believe, the stoichiometry stuff. It should also cover like the redox stuff and equations and types of reactions, I believe. So I think that's all the stuff that's on there. Again, the homework will be due on that day. Yeah, it will be posted. So Tuesdays is up there already. So today's will be up there. I don't know if it'll be tonight, but hopefully by tomorrow it should be up there as well. But Tuesdays is already up there, up online. So you should be able to find it. The homework will be due on that day. So again, you'll have to upload it. And just like the other exam, you'll have to obviously upload the work for those problems that have work associated with it. Also a reminder for lab, I'll take a little break and I'll open up the lab session in case anybody has some questions. But again, you should be working on the titration experiment, which will be a formal lab, and it's due, I want to say next week. I could be wrong, but whatever the due date is there, make sure you work on that. Next week, we will be rolling into, I think, the gas experiment. There should be 3 parts to the lab, if I'm not mistaken. There should be 3 different videos, one for part 1, one for part 2, and one for part 3. I think all 3 videos should be on that page. There is 3 parts to the experiment, unless I messed up, but I think there should be 3 videos. He might have did part 2 and 3 in one video. I'm trying to remember, but I think there are 3 separate videos. I'll double check, but there should be 3 separate videos. They all should be linked on the same one. I'll double check though, but there's definitely 3 parts to the experiment for sure. There's part 1 where you standardize your sodium hydroxide. There's part 2 where you do an acetic acid titration, and there should be part 3 where you do an unknown acid. And again, I thought it was 3 different videos, but it might be 2 where he did both parts in the second one, but I'll double check. I think there should be 3. Other questions on any of that stuff or anything that's going on? So like I said, next week we will be rolling into the gas labs, I believe. So that's what's on tap for next week. And in terms of labs, so make sure, again, you're working on the titration experiment. Again, if you have any questions, let's see, it's 7, maybe about 7:30, I will open up the lab session. Again, if you have any questions, feel free to come by and ask them. Again, make sure you come in through the lab link and stuff like that. Any other questions on anything? And I'll double check the videos just to make sure I didn't accidentally forget to put one up there, but there definitely should be 3 parts. All right, if everybody's good, again, if you have questions, please come. And again, it will be open about 7:30. Take a little break and stretch. And again, if you're not, make sure you're studying and have a good weekend and all that good stuff as well. And I'll see you next week if I don't see you later tonight.